Hello, 7.5 is complex numbers. So first, we define I for imaginary. I equals the square root of -1. And we use this because some mathematician a long time ago made it up, so we get to use it. Okay, and so if I is square root of -1, then I squared is -1. So if we look at the square root of -16, we can rewrite this as the square root of 16 times the square root of -1. We actually have to, okay, sorry, totally my fault. Square root of 16. Square root of 16 is 4, square root of -1 is I. So our answer, simplified, is 4I. For square root of -32, so typically how I think of this, we're really pulling out a square root of -1, but I just kind of think of this negative. And so we'll rewrite this as square root of 32, and that -1 we just pulled out of the square root is an I. And so now we have to look for perfect squares, okay? And so the biggest perfect square that goes into 32 is 16. So I can rewrite square root of 32 as square root of 16 times square root of 2 times I, which is 4 square root of 2 times I. 5I squared, a couple ways to do this, but if we distribute that squared, we get 5 squared times I squared. I squared is -1, so we get 25 times -1, which is -25. A complex number is in the form a plus bi, where a and b are real numbers and I is the square root of -1. Okay, so 2 plus 3i, 6 plus 8i. So for example 2, if z is 4 plus 5i, and w is 2 minus 3i, if we do z plus w, that means we're taking 4 plus 5i plus 2 minus 3i. And from here, we're just combining like terms. Okay, so we're going to treat I just like any other variable, except for I squared is -1. So we have 4 plus 2, which is 6, 5i plus -3i, which is 2i. So we get 6 plus 2i. If we were to do z minus w, we have 4 plus 5i minus 2 minus 3i. And we can distribute that negative. So we have 4 minus 2, which is 2, and we have 5i minus a -3i, which is 5i plus 3i, which is 8i. Now when we multiply z times w, so that will be 4 plus 5i times 2 minus 3i. Again, for now, we're just going to distribute and treat it like any other variable until we get to an I squared. So 4 times 2, and I want to kind of clarify I is not a variable, right? But in terms of operations, until we square it, we treat it like any other letter, even though I technically has a specified definition of square root of -1. Okay, so we have 4 times 2, which is 8, 4 times -3i, which is -12i, plus 5i times 2, which is plus 10i, minus 15i squared. And whenever I see an I squared, you saw it, I think I did it up above, I just circle it and say -1, because that's what it is. I do it right away. So then we have 8, -12i plus 10i is -2i. -15 times -1 is a positive 15. So since 8 plus 15 is 23, this simplifies to be 23 minus 2i. Z over 2, well, z is 4 plus 5i over 2. We can do, I call this the heart method, 4 over 2, which is 2, plus 5 over 2 times I. A pair of complex numbers in the form a plus bi and a minus bi are called complex conjugates. The complex conjugate of 5 minus 2i is 5 plus 2i, so all we're changing is that middle operation. The complex conjugate of negative 3 plus 2i is negative 3 minus 2i. Note, we don't change any other signs, all we change is that operation in the middle. So what happens here is that if a and b are real numbers, a plus bi times a minus bi equals a squared plus b squared. So for example, 3 plus I times its conjugate, 3 minus I, can multiply and get 9 minus 3i plus 3i minus I squared, which is negative 1. These cancel. We end up with 9 plus 1, which is 10. Point being, technically, if this is 3 plus 1i and 3 minus 1i, we can just do 3 squared plus 1 squared to get our answer. So if that shortcut makes sense to you, use it. Otherwise, we can multiply through. So whenever we have an expression like this, if you recall, we don't like to have radicals or roots, whichever you would name and prefer. We don't like to have those in the denominator because someone made up a rule at some point. Well, same with i's. We don't like i's in the denominator. And so in order to kind of fix that, we multiply by the complex conjugate on top and bottom. Okay? And the reason we're allowed to do this is because if you multiply by something on the top and the bottom of a fraction, technically you're just multiplying by 1. So you can multiply by 5 minus I over 5 minus I. So then we get 20 minus 4i minus 15i plus 3i squared. I squared is negative 1 over 25 minus 5i plus 5i minus I squared, which is negative 1. And so in the numerator, we end up with 20, and then 3 times negative 1 is negative 3. 20 minus 3 is 17. Negative 4i minus 15i is negative 19i over, let's see, the negative 5i and the positive 5i cancel, so we have 25. Negative 1 is 1. 25 plus 1 is 26. And technically, if we want this in a plus bi form, we have to write this, we have to split this and say 17 over 26 minus 19 over 26i. So in this case, for a plus bi, our a is 17/26, and our b is negative 19 over 26. Okay, here's another. Negative 3 plus 7i over negative 10 plus 2i. We're going to multiply by the complex conjugate of the denominator. And so negative 10 plus 2i goes to negative 10 minus 2i on top and bottom. So we have negative 3 times negative 10, which is 30. Negative 3 times negative 2i is 6i. 7 times negative 10 is negative 70i. 7 times negative 2 is negative 14i squared. I squared is negative 1. On the bottom, I'm going to shortcut it using that method we talked about. Because the middle terms will cancel out, we're going to end up with negative 10 squared plus 2 squared. If you want to go through and multiply negative 10 plus 2i times negative 10 minus 2i, that's totally fine too, and you'll get the same answer. So we have 30. Negative 14 times negative 1 is 14. 30 plus 14 is 44. 6i minus 70i is negative 64i. 10 squared is 100. 2 squared is 4. So we have 104. And so if we split it, we have 44 over 104 minus 64 over 104i. but we can definitely simplify. And if we divide everything by 8, no, for the first one, we can divide everything by 4, okay? And if we do that, we get 11 over 26. For the second term, we can divide 64 and 104 by 8, and we get 8 over 13i. Last piece for today is doing the quadratic formula, but we end up with complex zeros. So keep in mind in general with quadratics, we either have something like this, could be anywhere, but we have 2 x-intercepts, 2 real solutions. We can have 1 real solution, be up or down, or we can have no real solutions. And prior we would just say, well, we don't know the answer, right? No solution, no real solution. But now we can find it. So if there's no x-intercepts, they'll have non-real solutions. So if we subtract 5z on both sides to get this in standard form, we have 3z squared minus 5z plus 10 equals 0. Quadratic formula, z equals negative b, which is 5, plus or minus the square root of negative 5 squared, which is 25, minus 4 times 3 times 10, all over 2 times 3. So 5 plus or minus, this is 25 minus 120, which is the square root of negative 95 over 6. 5 plus or minus, I'm going to pull out that negative. And this is square root of 95i. We really can't simplify that square root, so all we can do is split it into our 2 pieces, and we have 5 over 6 plus or minus square root of 95 over 6 times I. One more like that. Quadratic formula, x equals negative b, which is 2, plus or minus the square root of b squared, negative 2 squared, which is 4, minus 4 times 1 times 7, all over 2 times 1. So x is 2 plus or minus, this is 4 minus 28, which is the square root of negative 24 over 2. 2 plus or minus, pull that square root of negative 1 out, so we have square root of 24i over 2. And so it looks like square root of 24 can be simplified, and it can. So we're looking for perfect squares, so we can take out a 4. So we can write this as 2 plus or minus square root of 4 times square root of 6, since 4 times 6 is 24, times I over 2. We're almost done. I'm going to go up here. So x equals 2 plus or minus 2 root 6i over 2. Divide everything by 2, basically just distribute that, right? We get 1 plus or minus 2 root 6i. And then we're done. And you have to fully simplify to have an answer be fully correct. One last thing I want to talk about. If you're asked to factor the binomial, we'll talk about this more when we get into more factoring. But essentially the pattern, if you have something like x squared plus 25, you can rewrite this as x in parentheses squared plus 5 in parentheses squared. So this actually factors into x plus 5i times x minus 5i. This is just a pattern, and you can multiply it through to prove it to yourself. You can also look at 6a squared plus 24. First thing you do when you factor, take out a GCF, so let's do it. You have 6 times a squared plus 4. And then since a squared plus 4 can be written as a squared plus 2 squared, plus, there's my 2 squared. This is technically 6 times a plus 2i times a minus 2i. So keep that in mind, but again, we'll talk about this more when we do more factoring in the next couple days.